Welcome back. This is the last recording of our series in Unit 3, the atom. And in this recording, we are going to talk about isotopes and ions and atomic forces. And we'll also cover some nuclear reactions as well. We already talked about isotopes a little bit in the previous section, but let's review those notes to get us off to a good start here. Isotopes of an atom are ones in which the number of neutrons are different. Of course, any atom of an element always has the same number of protons, but within an element you have different isotopes, and those isotopes will have different weights and therefore different numbers of neutrons. And so our example here is lithium-7, the isotope lithium-7. This top number is the mass number, which is equal to the number of protons plus the number of neutrons. And the bottom number is the atomic number, which is equal to the number of protons. So lithium-7 would have 3 protons and 3 electrons. It's a non-charged atom. And 7 minus 3 will give us 4 neutrons. So why don't you practice that skill for a minute, and then we'll get back together and discuss the answer. Okay, so if we were to write a nuclide symbol for uranium-238, we'd have the 238 is our mass number, and uranium has 92 protons, right? That's the atomic number, which is also equal to the number of electrons. And then we subtract those two. 238 minus 92 gives us 146. So we have 146 neutrons there. Okay, so let's do molybdenum-98. Molybdenum, I look on the periodic table to find the atomic number, and it is 42. So you have 42 protons, which is also equal to the number of electrons here. You subtract those two out and you get 56. Okay, so very good there. Okay, so let's talk about ions for a minute. Ions are atoms of an element with the same number of protons but different number of electrons. And you have two different types of ions. You have cations and anions. Anions have more electrons than their neutral atom and carry a negative charge. Nonmetals tend to gain electrons to have a full outermost shell. Thus, you can predict the number of electrons gained by their position on the periodic table. So, group 17 elements gain 1 electron and have a negative 1 charge. Group 16 elements gain 2 electrons and have a negative 2 charge. And group 15 elements gain 3 electrons and have a negative 3 charge. With this, you can look on the position on the periodic table and determine what type of ion that the element typically forms. And we're going to do examples of those. So I know I'm going rather fast, so pause the video and get caught up with all the notes here. And then we will talk about examples in the following slides. Okay, so here are some examples of anions. It says here group 15 gain 3 electrons and have a negative 3 charge. And it says a negative charge ion is called an anion. So these are examples, and we already talked about the tendency for each one of the groups. So fluorine typically forms a negative 1 anion. And when you look here at this example, you'll notice that fluorine always has 9 protons. Its atomic number is number 9. And so it will gain 1 electron and become a negative 1 anion, fluorine negative 1. Okay. And it's in group 17. So all members of group 17 tend to gain 1 electron to become like group 18 electrons, or 18 elements. Group 18 are the noble gases. And so all of them want to be, they're all noble gas wannabes. They all want to have a full outer shell of electrons. And notice here, if you add plus 9 plus a minus 10, you get a minus 1. Sulfur is in group 16, and so it will want to pick up 2 electrons to be like group 18 elements, and so it becomes negative 2. Arsenic would do the same thing, except it would gain 1 more, so 15 plus 3 gives you 18, so it picks up 3 electrons there. About cations. Cations are elements that have lost electrons and are positively charged. Metals tend to lose electrons to become positively charged. They tend to lose electrons to have a full outer shell. So group 1 elements lose 1 electron and become positively 1 charged. Group 2 lose 2. Group 13 lose 3 electrons to become positively 3 charged. And what happens here is that it takes less energy to lose the electrons than it would be to gain the number of electrons to become a noble gas type configuration or full outermost shell. So group 1 elements, we'll do examples here in a minute, become positively 1 charge, etc. If you forget this, you can remember a joke. There's 2 elements walking down the street, and they're happy as can be until one of them goes, oh no, I've lost my electrons. And the other one asks, are you sure? And he goes, I'm positive. So when you lose electrons, you become positively charged. That's not a great joke, but this is what I got. Examples here are sodium, calcium, and aluminum. Sodium's in group 1, so it loses 1 electron. So when it is sodium, it has 11 protons, and when it loses 1, it becomes like neon, or the noble gas that's above it on the periodic table. Group 2 loses 2 electrons. So calcium has 20 electrons, and when it loses 2, it has 18 electrons, and 18 electrons would be like argon. So, and aluminum loses 3 electrons to become like neon as well. And so when you have the when you have 2 elements, this is group 1, group 13 elements, this sodium and aluminum. Sodium losing 1 and aluminum losing 3 to have 10 electrons. If an element has different numbers of protons but the same number of electrons, it's said to be part of what they call an isoelectric series, and sometimes you'll see that mentioned in text. Nuclear forces. Okay, so this is one of those topics that is extremely interesting and super cool. There are internuclear forces that make the atom a very powerful phenomenon indeed. And one of these forces is called the strong force. Strong force holds protons to protons and protons to neutrons in the nucleus. And if you think about it, it's rather odd that you have this nucleus that has protons in it, because you would think those protons would automatically repel each other. And so the nucleus has to have this strong nuclear force to hold those protons together. And this force is about 100 times greater than the electromagnetic force. It's what they call a short-range force, because as the atoms get bigger and bigger, the protons start to repel each other. And so the atom will become less stable as it gets larger. As the atom gets larger, the protons start to repel each other. The same force that attracts protons to electrons in the atom is at work here. We call this the electromagnetic force. Okay, so within the atom, within the nucleus of the atom, you also have electromagnetic forces that repel positive particles. It's the same force that holds the electron in the atom. So in the center of the atom, where you have protons and neutrons, I'm not doing a great job of drawing here, but you have this positive force in the center of the atom. As the atom gets larger, those electrons start to repel each other, and of course also the electron, that electromagnetic force attracts the electron and holds it in orbit around the nucleus. So you have these electrons that are attracted to the positive force of the atom as well. And also within the atom you have something called the weak nuclear forces, and this changes neutrons to protons to obtain a more stable force. And so you have a situation, a dynamic situation, where you have larger atoms, and they try to adjust the proton to the neutron ratio, and they do that by changing neutrons to protons to obtain a more stable state. This force is not as strong as the strong force, but it also plays an important part in nuclear stability. This nuclear stability, there's two major factors. It's the size of the atom. Larger atoms tend to be more unstable, and also the proton to neutron ratio. For smaller atoms, this ratio tends to be 1:1, but changes as the atom gets larger to 2:1 and 3:1, etc. There is something called magic numbers, which means the number of protons and the number of neutrons in the atom are stable. And so there are certain mass numbers that tend to be stable because it has a good ratio for the size of the atom. And then what happens is when you have larger atoms, they undergo what we call nuclear decay, and to become more stable. So atomic radiation decreases the size, alpha radiation decreases the size of the atom. This is one of the types of nuclear decay that happens for the atom to try to become more stable. And in this alpha radiation, you'll notice here that the mass number decreases by 4 and the atomic number decreases by 2. And then it produces what we call an alpha particle right here. And so this particle is similar to a helium-4 nucleus, and it is the least energetic of the types of radiation that we'll talk about. We'll have alpha, beta, and gamma radiation as part of our nuclear decay or nuclear radiation series. So here it says in alpha radiation, the product is a helium-4 nucleus. The mass decreases by 4 and the atomic number decreases by 2. So you lose 2 protons and 2 neutrons. And we'll do some examples of those types of problems as we go along. Beta radiation changes the proton to, they change the proton to neutron ratio. In our example here is carbon-14. We see that the mass number stays the same, but the atomic number goes up by 1, and we get this beta radiation particle, or a beta particle, which is similar to a high energy electron. And so the product of beta radiation is similar to high energy electron. It changes a neutron to a proton. The mass number stays the same and the atomic number increases by 1. And we have a fission reactor here. In our previous slide we had a regular nuclear reactor, which is a fusion type of reactor. And we'll talk about more about those as we go through. So here we have a discussion of nuclear fusion and nuclear fission. Nuclear fusion is when 2 nuclei fuse together and massive amounts of radiation is released. And nuclear fission is when the nucleus split apart and massive amount of energy are also released. This reaction occurs in nuclear power plants. Fusion happens in the stars and in outer space, and you can also, people have tried to use nuclear fusion to create power. They haven't been tremendously successful, but they have some nuclear fusion reactors in different parts of the world, and they're trying to perfect that. Nuclear fission is when they split nucleuses, and this is what generally happens in nuclear power plants. You also have, as a result of nuclear reactions, something called gamma radiation, and this produces large amounts of energy. And we generally don't think of that as being a mass conversion, but as a product of some of these other reactions as a byproduct of nuclear fission and nuclear fusion. This is an example of a fission reaction where you have a neutron splitting an atom apart. A fission reaction where you have a nucleus splitting apart and creating lots and lots of energy. Okay, so here we have another topic here of half-life. When you have this nuclear degradation or nuclear reactions occurring, you also lose mass. So mass is converted into energy, and it does so in a predictable fashion, and we call this a half-life. And so the half-life is the time required for a reaction to reach half its original concentration. Examples of this, an example of this is maybe the half-life of a 100 milligram sample of an isotope. And its half-life is 50 days. So in 50 days, that 100 milligrams will become 50 milligrams. And in another 50 days, you'll lose half of that mass. And so our example here, we have 100 milligrams at day 1, and then after day 50, you have 50 milligrams, and we call that one half-life. After the second half-life, you'll have 100 days from the original starting point, and you'll have 25 milligrams, and so forth. And down after 4 half-lives, you're down to 6.25 milligrams of the substance. So you lose half in each step. And there are formulas that you can use to do this as well. One is the mass. So let's do the percent remaining one first. So it's the mass that you start with divided by n to the square. So n is the number of half-lives, and you square that, and then you divide that by your original mass. So here in our example where we started with 100 milligrams of a sample and go through 4 half-lives, if you take 4 and divide it by 4 squared, or 16, you would get 6.25% of your sample remaining. And so here in that example, it would be 6.25 milligrams since we're starting with 100. That would be 100%, right? 100% of your sample. You'd end up with 6.25 remaining. And then our next example is fraction remaining. It'd be 1/2 n. 1/2 raised to the nth, or to the n, of course, here is the number of half-lives. So in our example here, it'd be 0.5 or 1/2 to the 4th would give you 0.0625% of your sample left. So 0.0625 that would be the percentage times 100 would give you 6.25 milligrams.